Imagine you're trying to find the fastest route to work, but you only have yesterday's traffic data. What if your map thinks a shortcut is perfect, but it's actually under construction? That's the core challenge of offline model-based optimization, a critical tool in science and engineering where we must find optimal solutions using only historical data, not real-time experimentation. Let's say you're designing a molecule with specific chemical properties or optimizing an aircraft's aerodynamics. Testing every possibility in the real world is too costly, risky, or impossible. So we rely on surrogate models, mathematical approximations that learn from past data. But here's the catch. These models can overestimate performance in untested scenarios. It's like trusting a map that's accurate for familiar streets, but wildly wrong when predicting a new path. Enter quantum extremal learning, QEL, a quantum-powered technique that uses specialized circuits to identify optimal solutions in complex landscapes. QEL excels at finding peaks in high-dimensional data, but it's prone to overconfidence. It might declare a random point the best option, even if reality disagrees. So how do we make quantum models more cautious? That's where conservative objective models, COM, step in. Think of COM as a reality check. It penalizes predictions that seem overly optimistic, especially in uncharted regions of the data space. It's like adding a rule to your map. If you're unsure, don't promise a shortcut. Combining these approaches, researchers developed COM-QEL, a hybrid algorithm that merges QEL's exploration power with COM's caution. The result? A model that balances boldness with reliability. In tests, COM-QEL outperformed QEL alone, avoiding useless solutions while still discovering high-quality ones. This shows that even in the quantum realm, caution can be a superpower. But how does COM-QEL actually work? Let's dive deeper. At its core, COM-QEL uses a safety parameter called tau, which acts as a buffer between exploration and caution. When tau is small, the model stays close to known data. When it's larger, it takes bigger risks. Researchers set tau to 0.1, striking a balance between innovation and reliability. The algorithm also employs dual gradient ascent, a method that adjusts both the model's parameters and its safety constraints simultaneously. This is like having a team of experts. Quantum circuits handle complex pattern recognition, while classical neural networks ensure stability. Together, they navigate the trade-off between exploring new solutions and avoiding overfitting to noise. Testing COM-QEL on real-world problems, like optimizing chemical reactions or engineering systems, showed it outperformed older methods. For example, it avoided hallucinated solutions that other models generated, while still discovering novel, high-performing configurations. This makes it ideal for applications where safety is critical, like self-driving cars or medical diagnostics. Now let's zoom out. This isn't just about QEL or COM, it's part of a broader revolution in quantum machine learning, QML. Traditional machine learning relies on classical computers, but QML leverages quantum mechanics, unique properties like superposition and entanglement to process information in fundamentally new ways. For instance, quantum circuits can encode data more efficiently than classical systems, enabling faster optimization. A 2021 study showed that how classical data is translated into quantum states, called data encoding, drastically impacts performance. It's like choosing the right language for a quantum computer. Get it wrong, and the system can't understand you. Recent breakthroughs like quantum graph neural networks are pushing QML into uncharted territory. These networks could revolutionize fields from finance to drug discovery by modeling complex relationships in data. But challenges remain. Quantum hardware is still fragile, and scaling these ideas is a massive engineering hurdle. Still, the progress is staggering. Think of QML as the early days of the internet, full of promise, already reshaping industries. Whether you're an engineer, a student, or a curious viewer, this is a glimpse into the future of AI, a world where machines don't just learn faster but think differently. So next time you hear about quantum computing, remember, it's not just about speed. It's about smarter, more reliable decisions, even when the road ahead is uncharted. Thanks for watching. Stay curious, and we'll see you in the next episode.